In this section of chapter 14, we are going to discuss about some of the homework problems. This is Brown, Lemay, Barston book. Of course, you have Murphy and Woodward as co-authors. 12th edition, Chemistry, the Central Science. So our focus would be chemical kinetics homework. By understanding this homework, you would have the better concept, not only knowing the concept and also knowing the application of the concept. The first problem I'd like to go over would be 14.25 or problem number 25, page 600. And in this question, let me first read that question for you. The combustion reaction is given. Let me write down that reaction. 2H2. These are all gas phase. So just to save our space, I'm not going to write down G in the parentheses. Oxygen gas giving 2H2O. That's also gas. Now the question is, if hydrogen is burning at the rate of 0.48 mole per second. So hydrogen is burning means its concentration is dissipating. So I'm going to write down in kinetic terms change in concentration of hydrogen per unit time, and that burning at the rate of 0.48 mole per second. Now there are two questions in part A, and that's what we're going to do here. Part A is asking for what is the rate of consumption of oxygen. So basically they're asking for delta O2 by delta T, and also there's another part to it. What is the rate of formation of water vapor? Formation, that means concentration is increasing, delta of H2O by delta T. So we need to get these values. Obviously, first we need to write down how these rates are related to each other in terms of hydrogen, oxygen, and H2O. Let's first assume that all the rates are equal. Minus delta H2 over delta T. You know that there's minus because hydrogen is dissipating or being used up. Minus delta O2 over delta T. Oxygen is also, since it's a reactant, it will be used up in the reaction, but water is going to be formed, so it's going to be plus delta H2O over delta T. First, I wrote down these rates to be equal. That means rate at which hydrogen and oxygen are dissipating will be same as rate at which water is formed. But truly, they're not same, because as I mentioned before, with 2 here and 2 here, that means rate of dissipation of hydrogen will be 2 times greater than that of oxygen, because this stoichiometric ratio has to be maintained in a chemical reaction. So I mentioned that whatever is the coefficient, write down 1 over that number. So 1 over 2, that would be same as in case of oxygen is 1 over 1, because keep in mind this is 1 here and here you have 2. So this is 1 over 1 is 1, so this is going to be 1 over 2 because the coefficient is 2 for H2O. So now I set them equal. Now we already know the value because they have given you the value for minus delta HT by delta T. They're saying that the burning, hydrogen is burning at the rate of 0.48. So obviously this quantity is 0.48. So let me write down half of, so minus delta H2 by delta T, we are going to write down in terms of 0.48. And that's equals to minus delta O2 by delta T, and that's equals to half of delta H2O over delta T. Now, obviously, from here, our first answer would be what is the value for oxygen dissipation rate? So we already got that value. So that value I'm going to write down on the left so that you understand that minus delta O2 over delta T, and that's equals to 0.24. That's what we get from here. And the unit is going to remain the same, that's mole per second. So make sure you write down the unit so you know that how you express the rate. So we got this value from these two expressions. Now they're also asking about H2O. Half of H2O equals to half of H2O2. So you can just write down like this. You can cancel half and half. So the other way of thinking about it, water rate would be same as hydrogen rate. So it's going to be 0.48. But if you want to write down mathematically, it would be half of 0.48. That's for hydrogen. That's this number. That's this number. And that's equal to this number plus half of delta H2O over delta T. And from algebra we know that half and half would cancel out, so that would give me H2 delta H2O by delta T equals to 0.48. So my final answer is now already, we already got my final answer. Delta T equals to 0.48 mole per second change in concentration time. So let's highlight these answers. This is the rate at which H2O is being formed, and this is the rate at which oxygen is being dissipated. Now I'm going to do number 25B. That's on page 600. So let's do number 25B. Let me first write down the reaction that they're referring to. 2NO in the gas phase plus Cl2 in the gas phase, giving 2NOCl in the gas phase. Now they're saying that if the partial pressure of NO is decreasing, so partial pressure of nitrogen, you can write down as minus delta P for partial pressure. You can write down as concentration unit too, because it's the pressure change and concentration change would go on in a proportional manner. So if I have a smaller number of molecules, there'll be smaller pressure. Larger number of molecules or moles per liter, there'll be larger pressure. So change in pressure, that's what they're telling you. Change in pressure per unit time for NO equals to, they gave you the value, which is 56 torr per minute. Is 6 torr per minute. Now the question is, what is the rate of change of the total pressure? So you need to show the total pressure change. Now again, let's compare how these changes happening. I'm talking about in terms of rates of NOCl2 and NOCl. Again, I can set up a similar expression as we set up before. So minus delta PNO over delta T. I must have half in front because coefficient is 2, or it's dissipating 2 times faster. If I want to set it equal to that of chlorine, it'd be minus delta Cl2 P delta Cl2, pressure of Cl2 by delta T, equals to plus 1/2 change in pressure of NOCl divided by delta T. So basically I wrote down rates in terms of each of these substances, NO, Cl2 and NOCl. Since you have 2 here, that's why it's 1/2 here. So now we already know the value for NO is dissipating, so that means this value is known to be 56. So NO is dissipating at the rate of minus 56 torr per minute, because that's given. That's given. It's dissipating. Now, when NO is dissipating, Cl is also dissipating, but not at the same rate. So that value would be 1/2 of this number. So 1/2 of this number would be minus 28 torr per minute. So this number is due to NO, and the second number is due to Cl2, because Cl2 is dissipating half the speed of NO. So that's why it's half of that value. You can also understand it from this expression. Now, on the other hand, NOCl is formed at the same rate as the dissipation of NO. So it's going to be the same value. So it's the formation, half of NOCl, which would be equal to half of NO. So that means this is the same rate. Truly, NOCl and NO, the same rate. And that's 56 plus 56 torr per minute. Now this is for NOCl. What is the net effect? As you can see from clearly, by adding all these sum, it is going to be minus 28 torr per minute. So that's the net change, net pressure change. Let's review this problem. First, we found out, based on this value, this is given, 56 torr per minute is given, that's the rate at which NO is reacting. So Cl2 would be reacting half of that rate, because this half makes it equal to Cl2 value. So that half would be minus 28. So both are dissipating, so that's how pressure is changing. On the other hand, product is being formed at the same rate as dissipation of NO, and which is 56 for NO, so it has to be plus 56. So now you add up all these numbers to find net change. So the net change is going to be minus 28 torr per minute. That's the net pressure change because of this reaction. In this slide, I'm showing you how to do problem number 38. The reaction it is referring to is shown on the top, and basically they're asking you to find out this rate law. This is rate law. Once you know the A and B values, so these are the order values, then and also K value, then it becomes a rate law, because whatever concentration of reactants you have or you have in mind, you can plug in and you get the rate value, and that's why it's called rate law. So in order to get these A and B values, or orders of reaction, so what I did is I took 4 sets of data given in the book, and I came up with all these 4 different rate values and rate expressions. And you see that reactant concentrations are changing, 0.018 in first experiment, then it was 0.027 in the second experiment. So if you divide rate 2 by rate 1, so that means dividing this by this, you're going to get 1.5, because 3.9 times 10 to the negative 6 is the rate 2 given in the book for rate 2, and 2.6 for rate 1. Now why I've chosen like this? So that I get greater than 1, because that's easier for me to think about. So the ratio is 1.5, and on the right hand side what I'm getting is, you can see some of these numbers are identical, 0.036 on the top, 0.036 on the bottom. So let's cancel out. Now I have 0.018 the bottom and 0.027 on the top, and that gives you 1.5. KK would cancel out. So basically you get on the right hand side 1.5 raised to the power a. And on the left hand side, because we divided these two numbers, 3.9 by 2.6, we get 1.5. 1.5 raised to the power 1 is 1.5. So obviously a equals to 1, and that's how we got a equals to 1. This is order with respect to S2O8 is 1, or first order reaction. Now if you're going to divide expression 3 by 1, so this is my third expression, rate expression, and I'm dividing that by the first one. Again, I want to get larger than 1 by 1, that's why I picked these two numbers. Now that gives me 3 on the left hand side, and on the right hand side, if you look at this, my expressions on the right hand side, keep in mind these are based on the data they gave in that table in the book. So make sure you also look at that table in the book. Now here you can also get that 0.036 by 0.8 and 0.054 by 0.036. Now keep in mind, we already know a value, that's equals to 1. So this is 1, this is also 1. So that allows me to get divide these two numbers, which gives me 2, just from the left, this expression of left hand side. And then that's why we got 2 to the power a. The second set of numbers, top and bottom, that gives me 1.5. So I have 2 to the power a and times 1.5 to the power b. We already know the value of a equals to 1. So basically you have 2 times 1.5 b. So that's, you can write it down as 2 times 1.5 b. So you divide both sides by 2, that's why you get 1.5 on the left hand side, and 1.5 raised to the power b on the right hand side. So now 1.5 equals to 1.5 raised to the power b. That means b has to be equal to 1. Now in this case then, we got both a equals to 1 as well as b equals to 1. That means the rate, the order of the reaction with respect to S2O8 2 minus is 1, with respect to I minus is also 1. So now we got a rate law, can written down like this. We now have one more step toward the final solution. S2O8 to the power 1, I minus raised to the power 1. Now when I know the value of K, I can really plug in any concentrations to get the rate value. We are continuing this problem from last slide. Now remember that there are 4 rate expressions and the values. So I'm going to use one of those to calculate rate constant K. So this is the rate constant K for that particular rate 1. Now let me just copy that number. So rate 1 equals to, that's from last slide, 2.6 times 10 to the negative 6 equal to rate constant times 0.018, and we know by now order is 1, 0.036 order is 1, so that simplifies everything. And from this expression we can calculate the K value, and that's what you see like this. So dividing both sides by 0.018 and 0.036. So that's how we get K value for this rate expression 1 is 4 times 10 to the negative 3. In the same manner, use rate expression 2, 3, and 4 and get other K values. Ideally, these values should be the same, as because we have, this is referring to the same temperature experiment, but because each experiment has some experimental error, so the values would not be identical. So you take an average value, which is pretty close, 3.98 times 10 to the negative 3 is the average of all these K values that we can get from 4 sets of data or 4 rate expressions that we have in last slide. So we are going to use this as a K value. Now let's do part C now. In part C, they're asking you to find a relationship between rate of dissipation of S2O8 and compare it with the rate of dissipation of I minus. So basically look at this reaction on the top. There is 1 in front of S2O8 and 3 in front of I minus. So obviously to set them equal, I must have 1/3 here where the question mark is, this 1/3, and that would set them equal. So we can say the rate of dissipation of S2O8 is about 1/3 the rate of dissipation of I minus, and that comes from the balanced reaction. We have explained that before. So basically whatever you have as coefficient of balanced reaction, that becomes 1 over that value that goes with that particular reactant. So that's part C. In part D, they're giving you two concentrations of I minus and S2O8 minus, and you're supposed to calculate rate of disappearance of I minus. So let's first calculate rate of disappearance of S2O8 for those two concentrations that they have given. So S2O8 value is 0.025. So 0.025, that's molarity. And for I minus, the value is 0.050. 0.050. So we now know those values. And K value, we already know from part A, is 3.98 times 10 to the negative 3. Now we have all these values in order to calculate this value equals to, so you just multiply these three numbers. Let me have my calculator out and have this calculation. So first number is 3.98, then raised to the power minus 3, so that's the rate constant, times 0.025 times 0.050, and make sure you double check when I'm doing it. 4 point, so what I get is 4.975 times 10 to the negative 6. I didn't care much about significant figures, but if you want, you can keep three significant figures, because the rate constant we have is in 3 significant figures. And of course 0.025, even though they gave you 2 significant figures, you can consider it to be 250. But if you consider 2 significant figures, then obviously it would be 4.9, then you'd be adding 1 there, so it'd be 5.0, 10 to the negative 6. But anyway, the change is not going to be substantial. So what we got here now is the value for S2O8. Now we know the relationship, delta I to delta T would be 3 times larger. So basically you need to have, we have these values, we calculated these values. So basically you need to have 3 times the above value. So it would be 3 times 4.975 times 10 to the negative 6. What I get is 1.49 times 10 to the negative 5. That's the value for I minus. Now we are going to do number 46, page 602. This is the reaction of 2N2O5 in gas phase, giving 4NO2 and 1 mole of oxygen. So that's the reaction. They're doing it at 70 degrees centigrade and they're saying it's the first order reaction. I always write down the given information so that I can think better. It's a first order reaction, and rate constant is also given. I'm going to use the symbol used for rate constant, that's small k, 6.82 times 10 to the negative 3. That's per second. It's important that we write down the unit. I think in last slide I probably forgot to write down the unit for the rate, which is molarity per second. So in this case, k equals to 6.82 times 10 to the negative 3 per second. And they're saying that initially you started with 0.025 mole of N2O5. So the initial N2O5, this is, we call it A0, that's same as A0, so that we can apply the expression without any confusion. So that's N2O5 initial value is 0.025 mole. 0.025 mole, but in 2 liter. So we express molarity of concentration units. We're going to do that here. So divided by 2.0 liter, and that would give me 0.0125 mole per liter. Okay, so we have 0.0125 moles per liter. Now we are going to use this expression that we discussed before for first order reaction. So that's important for us to know. So log of, this is natural log of AT over A0 equals to minus KT. K is the rate constant and T is the time when the change had happened from initial concentration A0 to final concentration AT. Now time is given. They're saying the time is 5 minutes. So they're asking for that. This is 5.0 minute. I'm hoping that I copied these numbers with right number of significant figures. It is, I mean, they're just saying that how many moles of N2O5 will remain after 5.0 minutes. Obviously, they're asking for AT, or concentration of N2O5, not in molarity units, rather in mole units. So first we'll calculate molarity, and then from molarity we'll calculate moles, what the question is asking for. So we'll have to be paying attention to that. So I'm going to use this expression on the right hand side. So log of AT would be same as N2O5T. So I can write down N2O5 after T is the 5 minutes, and then N2O5 0, that's value is given, or we calculated that, minus KT. Now we can use the number now. K is 6.82 times 10 to the negative 3 per second. So that's K. And there's a negative value here. And T is 5 minutes. The minute doesn't is not compatible with seconds, so we have to change that to second. So 5 minutes times 60, that's 300 seconds. So that's what you're going to use in this calculation. So it'd be 300 seconds. Now per second, second would cancel out. Let's use a different color of the pen. So this second per second would cancel out. And that gives me a value of minus 2.046. Minus 2.046. Now, I'm assuming that all of you have scientific calculators, so take the inverse of this, inverse log or second function of ln, which is e to the power x. So that gives me N2O5 T divided by N2050, which we already know, 0.0125, and that's equal to minus, now I took inverse of, or second function of ln, and that gives me a value of 0.129. Make sure you double check all these calculations. So N205T, after 5 minutes, the molarity is 1.62 times 10 to the negative 3. That's moles per liter. Now remember, in order to get moles, I'll have to multiply that by liter. So in order to get our final answer, we are going to use N205, the final, in terms of, in order to get moles, it will be 1.62 times 10 to the negative 3 moles per liter times 2 liter, so 2.0 liter, and that gives me 3.24 times 10 to the negative 3 moles. That's how much N2O5 in terms of moles will be left after 5 minutes of reaction. So make sure you understand this calculation that I have discussed here. Now I'm going to do number 46, B and C. So number 46, B. And let me write down the reaction again. 2N2O5 giving 4NO2 and 1 mole of oxygen. Make sure double check this. 2N2O5, 4NO2, and 1 O2. Again, the rate constant is given, which is 6.82 times 10 to the power minus 3 per second. Now in part B, it's saying that how many minutes, you need to find out the time, how many minutes will it take for the quantity of N2O5 to drop. So basically they're asking for N2O5 concentration to drop to 0.010 mole. From obviously the initial value, I think we also write down the initial value, N2O5 initial was, again this is given in the question, was 0.0250. 0.0250 mole. So here all the given values, and based on that we can find out the time. Now you might have noticed that I didn't write down my concentration in molarity, rather I wrote down in moles. In this problem it's not going to matter. That was the case also with the last part. I think you're more experienced now, and I'm going to show you why it doesn't matter. So the expression that you're going to apply for first order reaction, we know that this is first order because they gave you that first order. So let me first write down the expression. Log of AT over A0 equals to minus KT. So molarity ratio would be same as moles ratio because you're dividing by the same volume, in this case 2 liter. So I could have done the problem, even the last part of the problem, just by taking the ratio of moles rather than molarity. So keep that in mind. So in this case we're going to save that time. So molarity ratio should be same as moles ratio. So that's why we're going to keep it the same as mole. Now let's plug in these values that we know. Log of AT, because the final they're asking for 0.010 mole. So I'm going to write down that 0.010 divide by the initial value 0.025, that's log, natural log, equals to the rate constant that's given minus 6.82 times 10 to the negative 3 per second. And here you need to find the time. So you need to solve it for time, and let's see what we get. Now log of, I'm assuming that you know this kind of calculations, first get 0.010 divided by 0.025 and take the natural log of that, and that would give you what I got by using my calculator is minus 0.916. You should double check. That's equal to minus 6.82 times 10 to the negative 3 per second times t. So when I'm getting the t value, that's what they're asking for, it'd be minus 0.916 divided by minus 6.82 times 10 to the negative 3 per second. Now per second becomes second now because you're taking inverse of that. So the value here is 134 second. And the question is asking for minute. So let's change it to minute. 60 second makes 1 minute. So that gives me 2.24 minute. Or I can round it off to 2.2 minute. So that's answer to part B. That's after 2.2 minutes, number of moles of N2O5 is going to decrease from 0.025 to 0.010. Now part C of this problem is quite straightforward. They're asking for what is the half-life of N2O5. Remember half-life when the concentration is decreased to 1/2 of its value? Now half-life expression for first order reaction is this: T half equals to 0.693 by K. So that's very straightforward. So 0.693, and we already know the value of K, which is 6.82 times 10 to the negative 3 per second. Let me double check whether I use my numbers right. Looks right. So this gives me 101.6. 101.6 seconds. Since the question didn't ask us in what unit we should get it, so I just kept it in second. So if you want to get it in minute, just divide by 60. That would give you answer in minute.